Hey, so today we're going to be taking a look at limits. In your textbook, we're looking at sections 1.1 through 1.4. We will initially move fairly quickly through the first two chapters. We've actually combined them into the first unit. It should all be review material, but we do want to make sure that everybody has a strong foundation in limits, continuity, and the basic differentiation rules before we move on and start looking at some of the more advanced concepts. So what I have for you to start with is a warm-up, and what I'll do is step out of the way and give you some time to think about the warm-up, write some stuff down, and then we'll come back and discuss the warm-up more in depth. Okay, welcome back. So the solution to the warm-up was really to get you thinking about limits, and we're going to go into a more rigorous definition of what a limit is in just a moment. But to answer the warm-up question, this is read as the limit of f of x as x approaches 2 is equal to 5. Okay? And is it okay for both of these statements to be true? Well, absolutely. I could have a hole in the function at 2 where the value of the function at 2 is equal to 3, but the limit is equal to 5. Okay. So next up, we're going to look at a more rigorous definition of limit and hopefully maybe make this click just a little bit more. Okay, so here we'll define a limit a little more rigorously, but in your textbook there is an even more rigorous definition of a limit using deltas and epsilons. It's not necessary to know that definition, but it may help some of you who are still questioning whether or not some limits do exist or not. We're going to say, I have two functions here, f of x in red and g of x in blue. One of them has a limit at 2 and the other does not have a limit at 2. Okay. For the blue graph, g of x, that does have a limit at 2, my formal definition of a limit says that I can take values of f of x along the y-axis close to L and still be able to find values sufficiently close to 2 that are still within the range of my function. Okay, and which is obvious. I can do that. I can make this what's called the delta neighborhood quite large, right? And I can make my epsilon neighborhood match that, and still every value within that epsilon neighborhood or the neighborhood around 2 is still within the range of my function. Okay. However, with the red function, there is no neighborhood or no distance from L that I can take such that every single value for a given neighborhood around 2 exists within the domain of f. Okay? In other words, I cannot take values close to a limit for the red function because I cannot make values of x sufficiently close to 2 without getting some neighborhood that's far too large. All right. So that's a little bit more of a formal definition of a limit, but I'm sure that the definition or understanding of limits that you have from pre-calculus will serve you quite well in the upcoming examples. Okay, so the limit laws in your textbook can be found on page 81. These are the basic properties of limits that you probably learned in you should have learned in pre-calculus, and that is that the sum of limits is the limit of the sum of functions is equal to the limit of the sum of the functions, and so on and so forth. And we're going to just demonstrate a few of those laws here real quickly. So given that the limit of f of x as x approaches a is equal to 5, and the limit as x approaches a of g of x is equal to -2, let's find these four quantities. So in a, it says the limit of f of x plus g of x. as x approaches a? Well, according to my limit laws, all I need to do is add 5 and negative 12. Excuse me, negative 2. Which is 3. Okay. For b, it's the limit of f of x cubed as x approaches a. Well, all I'm taking is 5 cubed. All right. And in C, the limit as x approaches a of the quotient of f over g. Now the assumption here is that the limit as x approaches a of g of x, or the denominator, is not 0. We know that's not the case here, but watch out because it might be. This is simply 5 over negative 2. And in C, the limit of 3 times g of x as x approaches a is just 3 times negative 2, which is negative 6, of course. I hope that seemed easy, because you won't have anything this easy on a test or a quiz. I guarantee it. Next, we'll look at a graphical representation of limit computation. Okay, one of the things to keep in mind in this class is that we're going to be looking at most concepts from 3 various points of view: graphical, numeric, and algebraic. We just looked at a numeric representation of limits. Now let's take a look at a graphic representation of limits. So what I have is the graph of 2 functions. Blue is f of x and red is g of x. And I'm asked to perform some limit computation. Fairly straightforward. I'm just getting my values for f of x and g of x, or the limit, from the graph. Whereas the previous example, example 1, let me label my example here. In example 1, I was actually given the numeric value. So that was a numeric example. This is graphic. So let's see. The first part A, I want the limit of f of x plus g of x as x approaches 2. So again, according to my limit laws, I can rewrite this as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And that's how I'm going to think about the rest of these. Okay, I'm going to neglect writing out this center step here for the rest of the examples, but that's what the limit laws allow me to do. So let's look at f of x. F of x is the blue function, and as x approaches 2, my limit is 2. The value of f of x at 2 is 1, but the limit is 2. And for g of x, it's 0. Okay. Moving on to b. Oops. I think this is supposed to be a 1. Otherwise, it's the same problem. It's just the first of many mistakes that you'll see me record and make. So let's see. The limit as x approaches 1 of f of x is 1. And the limit as x approaches 1 of g of x, looks like it doesn't exist. So we'll write D and E for does not exist. Okay? And 1 plus does not exist, does not exist. Alright. Example C. F of x times g of x, and we're looking at x going to 0. Alright. So as x goes to 0, f of x goes to 0, g of x goes to something. It doesn't really matter because it's 0 times something. It's just 0. The limit as x approaches negative 1 of f of x over g of x. So negative 1, f of x looks like negative 1, and g of x looks like 0. There's that instance where I said that could come up with it, where the bottom function comes out to be 0. In this case it does. So this does not exist. There is no limit. The limit does not exist. Okay. So in this example here, we have just think of the first function as the limit as x approaches 2 of x squared. Well, that's 4. Then we can go to my graph, and as f of x approaches 2, as x approaches 2 of f of x, I get 2. So 8. And the final problem, the limit as x approaches 1 of the square root of 3 plus f of x. Well, let's see, f of x is the blue one, so we get 1, and we get the square root of 4, which is obviously 2. Okay, so we've looked at a numeric example or representation of limits, and this was our graphical representation of limits. We're going to say that the algebraic representation of limits is really just the computation involved. So here's a more algebraic representation of limits. We have a function that's defined piecewise, and we're asked about whether or not the limit exists at 4. So does the limit as x approaches 4 of f of x exist? Okay. So think about this for a minute to yourself. You can pause the video if you'd like. So hopefully most of us said yes. And maybe a reason you said yes was you plugged in 4 to both parts, and at 4 the top part is equal to 0 and the bottom part is equal to 0. So we know that from the left and from the right of this function we will eventually meet at the same spot. Okay, so yes, the limit does exist. However, is it true that f of 4 exists? No. Okay. So, a very simple algebraic representation of limits. Alright, so in this example 4, initially I had 4 problems. I'm just going to do these 2 problems. In the notes that you printed off, there are 4 problems. I really just want to take a look at these 2 examples because this is stuff that you should have from pre-calculus. Okay, so I'm going to work these 2 guys out. If you have questions tomorrow on the other 2 examples, you're more than welcome to ask, and I'll be happy to discuss those. But they should be fairly straightforward. So let's see. Let's start in here. I see that I have something that looks like it might be factorable. So let's give it a try. Let's see. X plus 3 is a good guess. And look at that. X minus 4. It does factor. Lucky us. Okay, the x plus 3 factors cancel to 1. And I'm left with the limit as x approaches -3 of x minus 4, which is simply -7. Okay, moving on to B, rationalizing your denominator. Right, this is a skill from Algebra 2. Introducing the limit was in pre-calc. This is basic stuff for us in pre-calc or in BC. So let's run through this real quick. We're going to multiply top and bottom by the conjugate. In this case, it's the square root of x plus 1 plus 2. Okay. The reason we do that is because this expansion works out nicely and leaves us with x plus 1 minus 4, okay? Which is x minus 3, so these two factors cancel to 1, and I'm left with the limit as x approaches 3, the square root of x plus 1 plus 2. Well, the limit here gives me 2 plus 2 is 4. Okay, again, if you have questions about the other two examples, feel free to ask tomorrow, but I'm not going to take the time here to work those out. Okay, so switching gears a little bit here, I do a warm-up at the beginning, and every now and then I like to break the monotony of examples and problems and have you think to yourself a little bit. So think to yourself, how would you describe the end behavior of the following two functions? Y equals 1 over x and y equals 1 over x squared. Try using the word limit in your definition or your description. So take a moment, think to yourself, maybe write something down. Okay, so I'm hoping that some of us were able to use the word limit and infinity. So we might say that the limit as x approaches infinity of 1 over x is equal to 0. And the limit as x approaches infinity of 1 over x squared is also 0. Okay? We're going to use these two facts to help us solve limits in the next few examples. And we could actually have used these in the first part of example, I think it was example 4 that we just did. All right, so I went ahead and wrote those two factoids, if you will, at the top of the whiteboard here. And the first thing we're going to look at is this function f of x, x squared minus 4 over x squared plus 2. And I'm interested in what its limit is as x approaches infinity, so as x gets very, very large. All right? And you might know, using your Algebra 2 skills or powers of intuition, but we're going to look at a rather more rigorous way of coming up with that limit using some algebra and these two notions up here. Okay. So the first thing I'm going to do is I'm actually going to multiply the top and bottom by 1 over x squared, and you'll see why in just a moment. All right. So multiplying the numerators, I now have x squared over x squared minus 4 over x squared, and x squared over x squared plus 2 over x squared. All right. Well, simplifying things a little, this is 1. And now, if we know that this is just 4 times 0, and this is just 2 times 0 as the limit of x, or as x goes to infinity, then I really just have which some of you may have found by using your end behavior rules from Algebra 2 and noting that my exponents were the same and therefore should have been the ratio of my coefficients. And that works too. Here's a little bit more of a rigorous way to write that out and prove it to yourself. to wrap things up for the day, I wanted to look at two more special limits that may or may not come up, but if they do, you need to be prepared. I'm hoping that you got this in pre-calc, these two ideas, but if not, here they are. You can prove it to yourself by graphing the functions and looking at the limits. Or later in the year, we'll be able to prove it using L'Hopital's rule, which you may or may not have heard about. So let's go ahead and look at A. A is sort of looking like the first rule here, except that my denominator is not the same as the argument in the trig function. So let's make it look like the argument in the trig function. And we'll do that by multiplying by 5. Now that my denominator and the argument in the sine function are the same, I know that this limit as theta approaches 0 is 1, and I'm left with 5 times 1, which is 5. Okay. This piece is the rule. Right? In B, I can sort of see how these two are going to be similar. I got to get that cosine and that 1 to switch places. A good way of doing that is by multiplying or dividing out a negative 1. And we'll say we're not multiplying, we're dividing out negative 1 so that those signs flip. Okay. Now, what I want is 1 minus cosine x over x, but what I have is 1 minus cosine theta over theta times cosine theta. So we need to get that out of the denominator. Luckily for us, there's only multiplication going on here. And I can simply break that denominator up. So we'll say we have a 1 minus cosine theta over theta times 1 over cosine theta. Now, that's the rule. That's still a negative 1. And the limit as theta approaches 0 of cosine is 1. But it doesn't really matter because that's 0, and anything times 0 is 0.